Hello everyone. Today I will present Quality Diversity Actor-Critic or QDAC, an open policy actor-critic method for learning high performing and diverse behaviors within a single skill conditioned policy. I will first explain why multiple solutions matter, then define the user specified skill space, and finally connect the desired skill to QDAC's value and successor features critics. Suppose the objective is to move forward as quickly as possible. Walking, running, sidestepping, or moving while facing backward can all pursue the same objective. Task objective and behavior style are therefore not identical. Standard RL usually keeps only the highest written solution. QDAC asks why we should discard the other good ones. The point is not diversity for its own sake. And these alternatives matter when the environment changes. The fastest policy under normal conditions may no longer be best after a joint fails or friction changes. With a repertoire of distinct gates, the agent can select one better suited to the new condition without retraining. This is functional redundancy, alternative capabilities available when the nominal behavior fails. To learn multiple behaviors, however, we first need to define what makes them different. To collect multiple solutions, we first decide which differences count as behavioral differences. In the paper, the task provides four feature types: planar velocity, body heading, feet contact indicators, and the height of the lowest foot. QDAC does not discover these semantic axes automatically. The designer specifies the time step feature function and the skill space, which is the behavior descriptor space in standard QD terminology. QDAC then learns concrete policy behaviors that realize desired feature averages in that space. At each time step, we can record whether a foot is in contact with the ground as 0 to 1. The 10-step average shown here is an empirical illustration of the policy's long-run expected feature. A value of 0.6 means that the foot is in contact for roughly 60% of the time. This construction requires careful design. The mean must have a behavioral interpretation. Distance in space Z must represent a meaningful behavioral difference. And the targets should be feasible under the dynamics. If temporal order matters, the average alone is insufficient and phi must be redesigned. Each trajectory now has two relevant quantities: task return and observed skill estimated from each feature average. Standard RL usually searches for one high return solution. QD instead seeks high-performing solutions across a predefined skill space. For instance, it can learn gates with contact rates near 0.2, 0.5, and 0.8 while making each gate move quickly. The researcher defines the skill axis. Learning determines the concrete behavior that realizes each desired skill. QDAC implements this objective with one skill conditioned policy, although it does not guarantee a global optimum at every point. Within one training run, the task reward, feature function phi, and skill space z remain fixed. The algorithm samples a desired skill Z from space Z for each episode, and all sampled skills share one policy's parameters. The humanoid and ant examples on the right are therefore separate task feature experiments, not commands handled by the same cross-embodiment network. In this paper, each new task feature combination is trained separately. The feature average produced by a rollout is the observed skill. During training, we first chose a desired skill Z in the same space. For example, Z 0.10 to 0.6 requests a 10% contact rate for the first foot and 60% for the second. We feed Z into the policy and train the expected features to lie within tolerance delta of Z. Thus, user-defined point in skill space functions as a continuous command. The paper calls the skill, and the corresponding conditional policy mode is the behavior that executes it. At every time step, the policy receives the current state S and the desired skill Z sampled for that episode. The model-free implementation condition of shared actor on the observation and normalize the skill vector, then outputs distribution over motor actions. All skills share the same network parameters, but changing Z can select a different action in the same state. That is how one policy represents multiple behavior modes. Each dimension of Z has a predefined meaning and unit, such as contact rate or velocity. For every desired skill Z, QDAC imposes a constraint. The expected feature must lie within tolerance delta of Z. Subject to that constraint, it maximizes task return. In the body heading task, for example, Z is encoded as cosine and sine of the heading angle, while the slide displays degrees of readability. The agent should move quickly in the positive X direction while executing each requested heading. The next question is how a long-run feature target can guide an action chosen at the current time step. Suppose the desired contact rate is Z. Z is 0.6. At the current time step, phi t is either 0 or 1. Directly matching phi to 0.6 at every step makes both values look wrong and favors only instantaneous corner skills, such as always or never touching the ground. This behavior appears in the paper's no SF evaluation. The actor therefore needs a prediction of the future feature occupancy that each current action will produce. One action changes two future quantities, task return and the discounted accumulation of behavioral features. Conceptually, the paper uses a value function critic for return and a successor features critic for skill execution. In the practical model-free SAC implementation, the return critic is an action conditioned Q network. Because return alone cannot tell whether the future feature vector will match Z, QDAC learns both predictions and lets the actor use both when selecting an action. Successor features have the same structure as a value function, but they accumulate the feature vectors instead of scalar rewards. This psi estimates the discounted future features after taking an action in the current state. Multiplying psi by 1 minus lambda gives a normalized discount feature prediction. It is not literally the undiscounted trajectory mean. Rather, QDAC uses it as an action conditioned proxy for whether future behavior will execute Z. This converts a long-run skill objective into a signal that can evaluate the current action. QDAC learns two different predictions. The return critic predicts expected task return, while the successor features critic predicts discounted future features. The actor uses Q to improve performance and uses the SF term to reduce the distance between each normalized feature prediction and the desired skill Z. Both critics evaluate actions from the same actor, so each action can judge from two perspectives: task performance and skill execution. The paper evaluates 6 task feature combinations across worker, ant, and humanoid using 10 random seed replications and reporting the interquartile mean with 95% confidence intervals. Each aggregate headline is 15% more diverse behavior and 38% higher performance than the QD baselines evaluated with distance to skill and performance metrics. QDAC uses a continuous semantically defined skill Z to select the behaviors from one policy while optimizing return for each skill. But the designer must specify what phi and Z mean. The feature average and metric need behavioral meaning, and the experimental target ranges come from the task design. A new task feature setting is trained separately in this paper. Averaging also discards temporal order, which is a mathematical limitation of this representation rather than an explicit claim by the authors. In short, QDAC learns how to realize each skill. It does not discover what the skill coordinates should mean. Thank you for listening.